question that was on the homework quiz?
I think so.
Could you do 29?
I have a question.
Yeah, 29 just like a grind, right?
Yeah, I just couldn't, I don't know.
Let's see.
Sorry,
there's a few more.
Oh, that's okay. Jacob, Talika, Rita.
We did sign
Oh,
up.
yeah. You give me mine.
Make sure you don't take somebody else's.
MSU.
I'll go. Why not?
I mean, send out. So.
All right. So let's try this. Where did my stylus go? Stylus, where are you? There you go. Okay. Right? So just apply my definition. So f of t is going to be 2t plus h plus 1 over, oops, come on, Mr. Kulik, what am I forgetting? Limit. Okay, so I'm going to have 2t plus h over t plus h plus 3 minus 2t plus 1 over t plus 3 all over h. So far, so good. What I'm going to do next is I'm going to just multiply the top and bottom by what would be the common denominator in that numerator. And that'll probably simplify things a little bit rather than trying to make a common denominator and then like worry about adding those fractions and then worry about combining like terms and like multiplying by the reciprocal and all that jazz. This will just knock this down to just a fraction instead of being a complex fraction straight away. So when I multiply this in, the 2 or the t plus h plus 3 factor cancels with the denominator there. So I'm just going to have the numerator 2 times t plus h plus 1. Forgot to write the plus 1 there. Times the t plus 3. And then when I multiply into this one, the t plus 3 cancels, so I just have the numerator times the t plus h plus 3. And then this stuff is over h times t plus h plus 3 times t plus 3. Oops, and these t's were supposed to be a's, weren't they? How come nobody yelled at me? You guys are supposed to do that before I get like half the thing written down. So I don't have to change all this stuff. You guys really boogered that one for me. Thanks. Got about 100 t's to change out now. Because the problem wanted f prime of a, right? So like whatever t, a, what's the difference? Shouldn't make a difference, but let's follow the directions. We'll use a's. Okay. So up here, this is 2a plus 2h plus 1. So now we just got a lot of like really crappy foiling to do here. So 2a times a is 2a squared. 2a times 3 is 6a. 2h times a is 2ah. 2h times 3 is 6h. And then 1 times a is a, and then 1 times 3 is 3. And then over here, 2 times a is 2a squared. 2 times 8, or 2a times h is 2ah. 2 times 3, or 2a times 3 is 6a. And then 1 times a is a. And then 1 times h is h. And 1 times 3 is 3. And then that negative sign I'm going to just push through now rather than rewriting it again. Yeah, okay. And that's all over h times a plus h plus 3 times a plus 3. Okay, let's look to see if there's some like terms that we can combine. So I have a 6a and a negative 6a. I have an a and a negative a. I have a negative 3 and a positive 3. I have a negative 2a and a positive 2a. And then I have a negative 2ah and a positive 2ah. So I'm left with what I have 5h on top, right? So reduce those h's. Let's see where we're at now. So we have the limit as h approaches 0 of 5 over a plus h plus 3 times a plus 3. And when I do my direct substitution, I have 5 over a plus 3 squared. And I think that's our answer.
I think I just got lost.
Yeah, it's like
It's
an alphabet soup of like
Yeah.
a lot of stuff to write out if you're not careful with your foiling. Like it's easy to get turned around in there. If you didn't do this clearing fractions things, this gets really messy. Does it feel like there's got to be an easier way to do this though?
Yeah. Is there? Oh,
Yeah, much easier way, and it's coming. Chapter 3 is all about what are the shortcuts to doing this? Because this is terrible.
Yeah. It's a lot.
Which is great news, right? Isabel.
On the test, like in the future, would you make us solve it out like this, or can we just use the shortcuts to solve it?
It kind of depends on the context of the problem. There's some places where you just can't get away with not doing it this way, but for the most part, yeah, you would use the shortcut kind of whenever possible, unless you're specifically directed not to, or, you know, like you need to, you know, because of the context of the problem, there's no way around having to do this. But in general, yes, do the shortcut. Anybody else? That one was brutal. Thanks for asking. Isabel. 22? Oh, sure. This one sounds scary, but it's actually like relatively straightforward when you like realize what you're reading. Yeah, I know. And you're like, Mr. Kulik, this was not straightforward. It is after you've done like one or two like this. So let's take a look. So it's asking me to draw a graph, a possible graph, right? Your answers could vary. So it says g of 0 equals g of 2 equals g of 4, which equals 0. So what that tells me is that 0, 0 is a point, 2, 0 is a point, and 4, 0 is a point. Everybody's good with that? Okay, so I'm going to cross that out because we took care of it. It says g prime of 1 equals g prime of 3 equals 0. So what it's saying there is the slope of the tangent line to g of x is 0 when x is equal to 1 and when x is equal to 3. What does the graph look like if it has a tangent line with slope 0? It means that it's going to have a maximum or a minimum, right? Where if I drew a tangent line on that, it would be a horizontal line. So I don't know which one is which. I'm just going to put like something that'll be like a maximum or minimum that I'll connect to when I figure out which one it has to be for each of those two spots. Well, we got that basically figured out now. It says g prime of 0 equals g prime of 4, which is equal to 1. So that's telling me again, the slope of the tangent line at 0 is 1. And the slope of the tangent line at 4 is 1. So I'm just going to draw like part of my graph where that's like my tangent line. But that part's now done. It says g prime of 2 is negative 1. So again, at that spot, I'll draw a negative slope. It says the limit as x approaches positive infinity of g of x is infinity. So just end behavior going up. And as it approaches negative infinity, it's negative infinity. So the end behavior going down. And I'm just going to kind of connect. So I guess we got to go up to that one, down to that one, and there's my picture.
So other 2 points don't mean a lot.
Well, I didn't know whether I was going to have a max or min there, right? So I drew both of them because I wasn't sure which one I was going to be connecting to. But because of the slopes at 0, 2, and 4, it made it really obvious that, like, hey, between 0 and 2, I have to be going up to a maximum because, you know, the one side we're going up like this and the other, you know, like if they're doing this, well, we got to be going up here sometime. Let's go to that one. But that's the idea. And again, once you've done one like this, it's like, oh, that wasn't even hard. But like, what do I do with this the first time is not obvious, right? But like when you do it, it's like, oh, I could do that. It's not bad. And I get the homework is hard because you're doing a lot of these things for the first time. And it's like, that wasn't obvious at all. I eventually ended up there, which is fantastic. But it took me a long time to come up with that. But now that you've come up with it, you could do it again in, what, half the time, a quarter of the time? You know, a tenth of the time, depending on how long you spent working on something like that or thinking about something like that. Because when you see it and you know what to do with it, it's like, oh, that was a 1-minute problem. But it's getting to the point where it's a 1-minute problem. That's the point of the homework, right? Anybody else? Tessa? 14, that's the rock problem, huh? Okay. All the physics students in the room probably read this and was like, yeah, I know what to do with this. Or maybe not, you know, like it feels different because you're in math class, even though it's not. All right. So it says if a rock is thrown upward on the planet Mars with velocity of 10 meters per second, its height in meters after t seconds is given by the function h equals 10t minus 1.86 t squared. Find the velocity of the rock after 1 second. So here we're looking for like h prime of 1, right? I'm not doing that part first because when I read part B, it asks find the velocity of the rock when t is equal to a. That's looking for h prime of a. I'm going to do that part first because once I have that answer, I can just fill in 1 for a and I don't have to do that stupid limit thing again. So why do it 2 times when I only have to do it 1 time? So I'm going to do it that order. I hope everybody's okay with that. You're like, Mr. Kulik, you clever man. I definitely did not do it that way, and it took twice as long because I didn't think to do that. All right, so when I plug this stuff in, and this is the long part, I think after this, everything is fairly easy. Everybody okay with that? Notice I flipped the signs on the F or the H of A piece because I distributed the negative. I didn't write it out. I just did it. Everybody's okay? All right, let's do some foiling and stuff. So I have 10a plus 10h minus 1.86a squared minus 2 times that is going to be 3.72 AH minus 1.86 H squared. And then we still have the minus 10A and plus 1.6 A squared. Still all over H. Good news is, though, I look at this, I have some canceling to do now. And the wonderful part about that is the only stuff's left is the stuff with H's in it, so I can reduce some of that stuff down. So I'm left with 10 minus 372a minus 186h. And when I do my direct substitution, I have 10 minus 3.72a. So up here, I'm just going to have 10 minus 3.72 times 1, or 628 meters per second, I guess. And I guess this should technically have a unit on it, huh? Meters per second. Does this feel okay so far, Tessa? Okay. C then asks, when will the rock hit the surface? So the height of the rock when it hits the surface is 0, right? So I just need to solve 0 equals 10t minus 1.86t squared. To do that, I'm just going to factor, so I can factor off a greatest common factor of t, and then apply the zero product property. So one solution is when t equals 0. That's probably the start before we throw the rock up in the air. And the other piece is going to be 10 divided by 1.86, whatever that number is. I don't really care. I'm just going to leave it as the fraction. Cool there? Tessa? Yeah. Okay. And the last part, part D, says, what will the velocity be when we hit the surface? Well, the velocity is just going to be the derivative. And when we hit the surface, we know the time that happens. That's 10 divided by 1.86. So I'm just plugging that in. So that was, what was it? It was 10 minus 372 times 10 over 1.86. So what's that? Negative 10 meters per second, I think is what that arithmetic comes out to. What was the worst part? Getting the derivative out of it, right? After that, everything was relatively easy algebra-wise. But again, that derivative can be kind of a bear. The good news is shortcuts are coming to make that process go from like a multiple minutes process to a multiple seconds process. The shortcuts are very good. They're very short, which is nice to know. Just hang in there. We got like one more lesson of still doing it the long way, and then it's on to the shortcuts. And we have a whole chapter of just like figuring out the shortcuts. All right. Let's talk about 2.8, eh? So 2.8, we looked at the derivative of a function at a fixed value a. So here, in this section, we're going to be looking at the derivative as a function. So instead of thinking about it as a fixed value a, we can do it at any we can do it with a variable x. So we just still have the same formula, just instead of a's we have x's. Is the process going to be any different? No, it's going to be the exact same process, except what you're left with now is a function in terms of x, right? So this is interesting to us. This is like the first time we're seeing this, where we have an operation that we do on a function, and it returns for us another function, right? So the input is our f of x, that's a function. The output is f prime of x, that's another function. And what that function describes is the slope of f of x at any value x. So you pick any value you want, the derivative, plug it into the derivative, it'll give you the slope of the tangent line at that value of x on f of x, right? Okay, so here's an example. It says the graph of the function f is given in the figure below. Use it to sketch the graph of the derivative. So here's what I'm interested in. I'm interested in the maxes and mins. What will the value of the derivative be at the max and mins? If I draw a tangent line for those points, what's the slope of that tangent line? 0. So when I'm drawing my f of x, I know at those x values, the derivative is 0. Everybody's okay there? Okay. Now that I've done that, I'm going to erase those spots. Now I'm going to look at each of these sections in between, and I'm just going to be looking at what the slope is doing. Okay? So in this first section, the slope is decreasing, and it's getting bigger as we move from left to right because it's becoming less negative, right? Everybody's okay with that? So we're negative, and we're slowly becoming less negative until we get to that x. Everybody's okay with that? And in the next section, what is our slope doing? It's increasing, right? And it's getting its steepest here in the middle, and then it gets smaller as we get close to the top, right? The slope is getting smaller. Everybody's okay there? I wanted to get rid of that piece in the middle, so we have something like that. And the next section, again, we're decreasing, steepest in the middle, right? So in the middle, we should be at the lowest spot, and then we'll come back to 0. And then the last section, we're increasing the whole way, right? And the steepest part is the end behavior. So it's just going to be like something like that. Is everybody okay with how we drew this? Notice that the only specific value I cared about were the maxes and mins, just because that's going to give me the x-intercepts for my derivative. And then everything from there, I'm just looking at positive and negative, essentially, where the derivative needs to be positive and negative, which should match up with where the function is increasing and decreasing. That feel okay? Isabel.
Wait, I'm just confused on like the very first part of the graph. So isn't it slowing down? It's turning into a curve. So then in the second graph, like why is that like speeding out? Or is it supposed to be straight, or is that?
So this is decreasing, right?
Yeah.
So it's the slope is most negative at this end, and it's least negative at that end. So what do we see here on the function, f of x? Most negative at that end, least negative at the other end. Does that feel okay? It's okay. All right. So here we're going to do find the derivative for x cubed minus x. So we do this, right? Now, I mentioned this, Pierce came and asked me a question. I mentioned this like expansion formula. That's helpful if you have, like we've run into a bunch of things cubed here, will become less important in a section or two when we can discard using this limit definition of a derivative. But for right now, that's helpful shortcut, which I'm going to employ right now. So x plus h cubed is x cubed plus 3x squared h plus 3xh squared plus h cubed, and then minus x, and then minus h, and then I have minus x cubed plus x. Uh-oh. Nobody yelled at me. Yeah. I know. That's why doing it on OneNote is so helpful, because I can just like pick it up and move it over. All right. Yes. Yes, of course. All right. Combine some like terms. Everything left just have h's in it, so reduce some h's. So we have 3x squared plus 3xh plus h squared minus 1. When I do my direct substitution, I'm just left with 3x squared minus 1 because all the h pieces drop out, right? Now it says compare the graphs. Isabel, I'm sorry. Go ahead.
Can you slow down like a little bit?
Yes.
Thank you.
Yeah, sorry. I just get excited about it. And then like the algebra is not hard for me, so I just like want to bulldoze through that.
Yeah.
Because it's just like all I'm doing is pushing symbols around, and it's not the point of this. The point is part B, to compare what's going on.
It's just hard to write and
Yeah, for sure. And here's the thing. Again, all the notes, everything I write are yours. So if it's hard to write and listen, maybe give it a go for a class or two just listening and seeing if that helps, and not trying to write everything down and rely on like, I have all of his notes. Maybe that, just see, right? It might work a lot better. I've been in classes where I gave up trying to write anything down. I just listened and things worked out much, much better. And I've been in class where I can write everything down and it's great. But, you know, you don't know like what's going to work. Isabel.
I just have one more question too.
Uh-huh.
So in the second part, what is the, like after the h cubed, what is the minus x minus h minus x cubed plus x?
So I have x plus h cubed minus x plus h, right? So this is that part. And then minus f of x is that part.
If it's minus f of x, why isn't it,
Because I distributed the negative.
okay.
All right, let's take a look at what this bad mama jamma looks like. So here's the original function, and I'm going to do a fat line for the derivative now. Oops. And then we'll just zoom standard that. So there's my original. There's my derivative. I'm going to mess around with my window here a little bit to get a little bit better picture. So there's f of x. There's f prime of x. Notice at the maximum, the derivative is 0. At the minimum, the derivative is 0. Where we're increasing, the derivative is positive. Where the function is decreasing, the derivative is negative. And where it's increasing again, the derivative is positive. That's the takeaway. Everybody's cool? Okay. Let's look at this next one. We have to do the derivative of the square root of x. And then it wants us to state the domain of f prime. Oops. So we'll start with our, say f prime of x is equal to the limit h approaches 0 of f of x plus h minus f of x all over h. So when I do the f of x plus h is just going to be the square root of x plus h. And then we have minus the square root of x all over h. How come no one's yelling at me yet?
You dropped the limit.
You got to do it sooner.
I dropped it too.
Okay. Everybody so far so good? What am I going to do with this? Yes! Good eye. We'll multiply by the conjugate, which would be square root x plus h plus square root x. Right? Isn't that screaming multiply me by the conjugate? I think so. So when we do that, we have x plus h minus x on top, and then h times square root of x plus h plus square root x on bottom. Those guys cancel out on top. And the h's reduce, so I'm left with just a 1 on top. And when I do my direct substitution, the h's go to 0. What's the domain for that function, that derivative there? Okay, good. So we know that because it's a fraction, the denominator cannot equal 0. And we know because there's a radical, the stuff under the radical has to be greater than or equal to 0. So if I divide by 2 and then square both sides, I have x cannot equal to 0 and x has to be greater than or equal to 0. Those two things can't happen at the same time. Because the not equal to 0 cancels out the or equal to 0, so you have just greater than 0. What do you notice about the function here, though?
Oh.
They're different. The domain of the derivative is smaller than the domain of f, right? F contains one more number in its domain than f prime does. Oh, okay. That's fine. That can happen.
Wait, what do you mean?
Well, it means that while I can do f of 0, right? f prime of 0 does not exist. Which is kind of weird, right? Think about why that's happening, though. If I think about the graph of f of x, it's this, right? How do I do the slope at that point when there's no graph coming into that point? The slope of the tangent line, when there's nothing coming in, there's nothing, there can't do a limit on. That's why we don't get a derivative at 0, because we don't have full continuity there at 0. Oh, okay. So somehow continuity and differentiability are going to be related? Seems that way. Let's keep going and do some more examples here. All right. So we have another one. Oh, yuckers. How much time does this class still have? 30 minutes? Okay. 35 minutes. Let me look. Okay.
Oh, wow. I think I see this one, yeah.
No. I just want to know if I want to skip this because it's just going to be like a pain in the tuchus. And we just did one like this in the homework.
Yeah.
Okay. You guys are good with doing that? It's just like a pain in the butt example. But it's just like, yeah, so it's going to be just like this one that we already did, number 29, because it's just another rational function. I think it's probably not quite as ugly as this one, but like it's going to be almost the same kind of, like the algebra would be the same. Yeah, do it for practice. I love it. The answer's in the book, right? Okay. So we're going to skip that. Okay. So, notation. Sure. So all of these symbols, all of these different symbols are saying the same thing. These are all equivalent ways of asking you to take the derivative. So if you're given a function notation, typically we say f prime of x. Or if you're given it as y equals, we can write y is just the derivative as y prime. But oftentimes, we're going to use this notation, dy dx. What does this kind of remind you of? Change in y over change in x, which is just slope, which is essentially what the derivative is. It's a slope function, right? It's a function that just gives you the slope of the tangent line at every point along your function. So we use the operator d dx as like our symbol that means we're doing the derivative. So like if I have y equals 2x plus 1, I could do like take the derivative of both sides. So if I'm like showing work, that symbol d dx is my symbol saying I'm doing the derivative of both sides. The derivative of y is just dy dx. The derivative of 2x plus 1, we do the limit stuff, you know, yada, yada, yada. Everybody's okay with just the notation there? The question should be in your head, it's like, why the heck do we have a million different notations for this? Big reason number one, calculus. Discovered independently by two separate people in different countries. Isaac Newton in England, Gottfried Leibniz in what would become Germany, I think at the time there was no German state yet. They did these, they did their work independently. They have two separate approaches to this, two separate notations. As things spread in the 18th century, communication was not instantaneous. So like in places like Russia that had very little contact with the West, you had whole new notations built around that worked in the country that they were working on for the specific context in which they were working, that were really convenient. And just we didn't discard them because it works. It's such a neat, compact way of, in this one particular instance, that we are left with all these extra notations. Okay, so it's just a matter of like the historical development of mathematics is why we end up with this. Absolutely. Okay. A function f is differentiable at a if f prime exists. It is differentiable on an open interval a, b, or even the unbounded intervals, a to positive infinity or negative infinity to a, or negative infinity to negative infinity, if it is differentiable at every number in the interval. Okay. Where is the function f of x differentiable if f of x is equal to x, or the absolute value of x? What's the graph look like? Let's start with some intuition. What's the graph of the absolute value look like? It's a V. Great. Everybody's good? What's the slope on this end? -1, right? What's the slope on this end? +1. What would the slope at 0 be? Nope. Pierce? Why? Well, if I look at the limit as h approaches 0 from the left of this, we get -1. The limit as h approaches 0 from the right of this, we get +1. So the limit does not exist at that point, hence the derivative does not exist at x equals 0. So what you're looking for is you want to make sure the slope on the right half matches the slope from the left half. That's all I'm looking at. If that doesn't happen, the derivative can't exist there. So notice, this is really interesting. F of x equals the absolute value of x. Continuous over all real numbers, but not differentiable over all real numbers. It's only differentiable from -infinity to 0, and then 0 to positive infinity, not differentiable at 0. So somehow continuity does not imply differentiability, right? And we saw that before, where the square root of x was continuous over all non-negative numbers, but only differentiable over the positive numbers. It wasn't differentiable at 0. That was a continuity issue. This, though, is continuous from the left and the right. We have no problem there. But we have this corner. So, here is our most important theorem from this section. If f is differentiable at a, then f is continuous at a. differentiability implies continuity. The converse is not true. Continuity does not imply differentiability. Your classic counterexample is the absolute value of x that is continuous over all real numbers, but not differentiable at 0. But if it's differentiable, we automatically have continuity. Elena.
So is that like what's the definition of like differential?
The derivative exists for all values on the interval. So if we say if it's differentiable at a, means that f prime of a exists, right? So like and continuity says that, right? Yes, certainly. Okay. The place where this theorem becomes most important is as a tool to justify what you can do or not do in a problem. If you have differentiability, automatically having continuity means that if you have some function you want to do the intermediate value theorem on, and you know that function is differentiable, you have the continuity piece for free then, right? You can just say, because the function is differentiable, I know it's continuous, and now I can use the intermediate value theorem.
How do you know it's differentiable, or like will
It would say in the problem, it'd be say like, for differentiable function f, yada, 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 and it'd be like, oh, look, it's differentiable, so now I have continuity, which is lovely. All right. So when does a derivative fail to exist? We've seen the case where we have a corner, right? That's the absolute value function we just looked at. We've seen the case where we have a discontinuity, like the square root of x, where it wasn't continuous from the left. The one we haven't looked at is if we have a vertical tangent. Anybody think of a function off the top of your head that has a vertical tangent to it? It's one you have seen before in Algebra 2. Not x squared. Not x cubed, but you're close. Cube root of x. That looks like this.
So does those tracks means that the derivative doesn't exist, or it does?
Well, I'm just saying that we looked at a corner, right? We've looked at a discontinuity, even though like technically that's continuous over its domain, but like we saw that the derivative failed to exist at 0 because we didn't have continuity from the left there. And then the one we haven't seen is the vertical tangent. Your cube root of x is your canonical example of something like that. Could there be other things? Oh yeah, sure. Yeah. But those are your classical examples. So far, so good? So again, this piece is like screams out multiple choice question, where we give you a picture and ask you like, where does the derivative fail to exist? So what are you going to look for in the picture? Corners, discontinuities, vertical tangents. You know, that's classic multiple choice question, right? Where I give you a graph and we ask you where the derivative fails to exist. And you're just looking for these 3 situations. Everybody's okay? All right. So what we want to talk about next are higher order derivatives. You can take the derivative of a derivative we call that the second derivative. Could you take the derivative of the second derivative? Yeah, what do we call it?
Third derivative.
And so on and so forth. How many times could you do this? As many as you want, right? Let's look at this example. So we did this already, right? We started off doing this at the beginning. We know that the first derivative, yes.
Scroll up for a second, just like copy down the.
Sure. So we did this problem already where we found the first derivative at the beginning of class, right? So if I want the second derivative now, that'd be the limit as h approaches 0 of f prime of x plus h minus f prime of x all over h. Still the same process, right? So when I plug x squared plus h into f prime, I get 3x squared plus 6xh plus 3h squared, and then minus 1. And then minus f prime of h is just going to be minus 3x squared plus 1 all over h. Ah! Yeah. You guys were so Johnny on the spot last time, and we have missed them all this time. And maybe it just means I'm going too fast for anybody to register. Sorry. How impressive is it that I can foil in my head this quickly?
Very.
Press the one.
I
can't even process it. Yeah, I don't even know what's going on right now.
So let's look at what can reduce. And now we can do the h's. Yep. Exactly right. So we have what's left? 6x plus 3h. Or just 6x.
How is this different from what we did yesterday?
Nothing is different. That's the point. Yes. All we're doing is instead of treating it as like the derivative at an arbitrary value x, we're just now making it a variable.
Oh, okay.
So instead of being like f prime of a, where everything's an a, it's just an x now. That's it. We didn't do anything. Same process. The algebra is identical, which is lovely, right? It's like, oh, like kind of a deep breath here. Not more complicated than last time. It's just the same thing over again with. All right. A classical example of derivative of like higher order derivatives is in physics, where acceleration is the first derivative of velocity, which would make it the second derivative of position. So if you think about position, that's in like meters, right? Velocity, meters per second. Acceleration, meters per second per second. That's why this is the one derivative, two derivative, and we'd end up at acceleration. There's actually a fourth thing. Does anybody remember what the fourth or the third derivative from position would be, physics people? Yeah, it's named after you. Jerk.
That wasn't easy.
No, but you'll remember it now because I made the joke. So that's like the third derivative of position. So remember our rock throwing problem from before. Remember the rock throwing problem from the previous homework, right?
Yeah.
We found the derivative to get the acceleration formula. If I did the derivative again, it would get the acceleration formula, right? Because we started with
So you found both.
position. First derivative was velocity. If I do it again, I would have gotten acceleration. Nobody asks about jerk, but it has a name though. And then the third derivative again, we've implied this already. So let's take our example, f of x equals x cubed minus x. Right? We found the first derivative was this. We found the second derivative was this. Let's find the third derivative. But this is great, right? Look at how simple our function is.
What's the highest one?
Well, hold on a second while you'll see what happens here. So I distribute the 6 through and I combine like terms. So that just turns into 6, right? What if I did this again?
Oh, so it's just like,
No,
oh, never mind.
no, no,
Apparently not.
It's gonna be half.
no.
Guys, let's just stop guessing. Like, we're not gonna get it.
So f of x plus h, when I plug that x plus h into the x on 6, what do I get?
What? Wait, sorry. What?
I'm doing, this is my f of x, right?
Oh.
I should put those guys on there, right? There. It's just 6, right? Because there's nothing to plug in.
Oh. But it's 6 over. Huh? Wait, Mr. Kulik, how did you get the 6 again? I'm like, 0. Oh, just because x or 6 plus 0 is 6? Oh, yeah.
Those reduced out,
Yeah.
and I'm just the limit of a constant is the constant.
So is that the highest that you can do then?
No. It'll depend on the function,
But whenever
but at some point, no, you could get 0.
Okay.
Wait, where did you get the 6s from again?
F cube or f triple prime is 6. So when I plug x plus h into the x here, there's no x to plug into, so it's just 6. F triple prime is 6, right? That's what we found in this step here, right? F triple prime is 6. So when I do f triple prime of x plus h, there's no place to plug the x plus h in. It's just 6, right? F of anything is just, or f triple prime of anything is just going to be 6. Because it's just a constant. What? So if I graph y equals 5, what's the y coordinate when x is 7? 5. What's the y coordinate when x is 20? 5. What's the y coordinate when x is 10 million? What's the y coordinate when x is x plus h? What's the y coordinate when x is x plus h? 5. Is that okay? Prater. 3-1.
I know that makes it all easier.
Yeah.
Skip to that.
I know. Everyone knows the power rule already. It's coming.
I want to learn the L'Hopital. Doesn't that make everything easier?
L'Hopital?
Yeah.
It is once you can do derivatives.
Oh, well, I can't.
Wait, why? You said everybody knows. All the
What? I mean, everybody knows the power.
That was smart. You're smart.
That's a new set. Oh gosh, is this when you do this Sunday? Yeah. Right?
No,
Oh.
because we don't have a class.
Oh,
right? So what's due on Sunday?
the old set,
2-1 and 2-7. 2-8 would be due
the following set.
following Sunday,
But then there's a homework.
but there will be a homework quiz, so you
That's
should.
next week.
But it will be next week, so you can worry about it next week, of course.
But it is Monday.
What?
So Sunday's homework is 2-1 and 2-7. This is 2-8, would be due the following Sunday. We will have a homework quiz on 2-8 next time. But here's the lovely part. What was different between
Nothing.
2-7 and 2-8? Almost nothing, right?
But there's more. Like there's more
It just
hours.
means you gotta do it twice.
Yeah, you have to do it twice now instead of once.
I don't ask you to do a whole lot of those. And here, what did you notice though about each time we did this? It got easier.
Yeah.
That's a feature of all polynomial functions. Each time you take the derivative, it should get simpler. Okay. How are we doing, folks?
A little tired.
I'm really tired. I don't know. Like today's just not good.
I did not sleep last
How is, okay, let me rephrase. I am super interested in how tired we are. That's not really what how is math going?
It's decent. I think I just need a lot of practice. Cause I know what to do when you do it, but I can't do it by myself. Like when I look at the problem, I'm like, I don't
Suck at factoring.
Yeah, I suck at algebra. That's my problem. Like I can't do the algebra.
And what did I tell you on the first day?
The
The hard part of calculus is the algebra, not the calculus part, right?
Yeah.
I wasn't even moving. It's just sitting.
Reserved 100.
Did I ask you?